Hello class, welcome back. In this video we are going to continue with chapter 4, section 2, addition rule and multiplication rule. So we are going to talk about the addition rule, which the key thing about the addition rule is it has to do with probabilities that either event A occurs, event B occurs, or they both occur. And the word or is associated with the addition rule. Then we are talking about the multiplication rule, and that's used for finding the probability that A and B both occur. So let's talk about a compound event. A compound event is any event combining two or more simple events. So whereas in section 4.1 we only talked about one event occurring, flipping a coin and getting heads, now we're talking about two or more events. So think maybe a deck of cards and you want to say the probability of getting a red card and a queen. Or we can say the probability of getting a jack or a 10 would be examples of compound events. So let's talk about addition rule. So first we'll begin with the notation. So the probability of A or B is really just saying the probability of, in a single event, event A occurs, or event B occurs, or they both occur. So an example would be, we want to know the probability of drawing a jack, event A, or a red card, event B, when randomly selecting a card from a standard deck. We have a success if we draw a black jack, a red card, or a red jack. That would be event A for a black jack, because event B wouldn't have occurred. A red card, which is event B, and it's no jack, so it's only event B occurring, or a red jack, meaning success for both events A and event B. To find probability of A or B, add the number of ways event A can occur and the number of ways event B can occur, but add them in such a way that every outcome is only counted once. What do I mean by that? Well, I'm going to show you an example in a little bit, but basically you'll find that if you add them in a way that you just add the two probabilities together, you'll actually be counting the probability of both of the events occurring once. You can't count the same outcome more than once. So here is the equation that we'll be using. The probability of event A or event B occurring is the probability of event A plus the probability of event B minus the probability of event A and B. Because if that event happens, you're already counting it for probability of event A and you're counting it for probability of event B. So you're counting the same event happening twice. So let's look at an example. Okay, when finding probability of drawing, we want to know the probability of drawing a jack or a red card. So it's addition rule because of the word or. So probability of a jack or a red is the probability of a event A, which is a jack, plus the probability of event B, which is a red, minus the probability of it being a red jack. So if in a standard 52 card deck, there are 4 jacks, so that's 4 out of 52, plus there are 26 red cards, so 26 out of 52, and then we have to subtract the probability of it being a jack jack and a red. Why do we have to subtract out that 2? And it's because it's redundant. There are 2 red jacks in the deck that we are already counting twice. I counted those red jacks when I did the probability of event A, and I counted those red jacks when we did the probability of event B. So I can't count them twice. I have to subtract them out. So let's look at with the cards highlighted. I kind of created this slide to kind of show it to you. So we are interested in a card being a jack or a red. So there are 1, 2, 3, 4. There are 4 jacks. There are also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 26 red cards. So I'm going to add those two values together, 26 plus 4, but I can't say that 30 cards are going to give me a success. Because if you count the total number of cards that give you a success, you have 28. Why is that? Because we need to subtract out 30 over 52 minus 2 out of 52. We cannot count these red jacks twice. So again, it's the probability of event A, which is 4 out of 52, these 4 right here, plus the probability of a red card, which is 26 out of 52, or these 13 plus another 13, 26 out of 52, minus, because we can't count these cards twice, minus 2 out of 52, gives us our final answer of 28 out of 52. Okay, now we will talk about disjoint events and the addition rule. So disjoint is a term that the book uses. I always called it mutually exclusive. And we say that events A and B are mutually exclusive if they cannot occur at the same time. That is, that they have zero overlap. So just two events that cannot happen at the same time. A boy and a girl cannot be born at the same time. A flipping a coin cannot be a heads and a tails. If you play a round of roulette, you cannot have the ball land on a red and a black on the same roll. All those events would be mutually exclusive. They cannot happen simultaneously. Okay, so let's just talking about further examples of that. An event cannot be event A, calling it randomly selecting someone for a clinical trial who is male, and event B is randomly selecting someone for a clinical trial who is female. The selected person cannot be both. And then an example of something that is not disjoint is event A would be randomly selecting someone taking a statistics course. Event B might be randomly selecting someone who is a female. The person can be both. So since those events can happen simultaneously, they are not disjoint. They are not mutually exclusive. So here is a summary of the key points of the addition rule. To find the probability of event A or B, just make sure you associate the word or with the addition rule. When you see the word or, that immediately should scream, addition rule. And then when you find later in the section, when we talk about and, it'll be multiplication. And then number 2, to find the value of probability of event A or event B occurring, you have to add the number of ways A can occur plus the number of ways B can occur, but just be careful to not count any event twice. You got to subtract out anything that's redundant. So subtract out the probability of event A and B occurring. Okay. Complementary events are as well. So we use a bar to indicate that the event A does not occur. We talked about this previously, where the complement of A is the A bar, and it's basically the probability that A does not happen. So we are certain, with probability 1, remember certain means 100% probability, that either an event A occurs or it does not occur. So it would follow that the probability of event A occurring or the probability of A not occurring would equal 1. So because they are disjoint, we can use the addition rule to express this principle. So the probability of event A occurring plus the probability of A not occurring equals 1, because it has to either occur or not occur. So then just some simple algebra can show you different ways of writing this equation just by moving things over. Subtract out the probability of A from here, or probability of complement of A here gives you these two equations respectively. So let's look at an example. Based on a journal article, the probability of randomly selecting someone who has sleepwalked is 29.2%, or 0.292. So the probability of sleepwalked is 0.292. If a person is randomly selected, find the probability of getting someone who has not sleepwalked. Well, if we know the probability of someone who sleepwalked, and we know that you either sleepwalk or don't sleepwalk, you can just do the complement rule. So the probability of a complement, which is someone has not sleepwalked, is going to be 1 minus the probability that that person has sleepwalked, which would give you an answer of 0.708. So that's it for the addition rule for now. Let's move on to the multiplication rule. And we'll talk about first a single trial, meaning just only doing one event. Next, we'll do multiple events. So the notation is the probability of event A and event B would be that the event A occurs and event B occurs in the same trial. So think of not a red or a jack, but now we're looking at the probability of it being a red and a jack. Remember that word "and" is associated with multiplication rule. And how do we solve these types of problems? You just have to do the probability of event A multiplied by the probability of event B. And that would give you the probability of both events occurring at once. So let's look at an example. Find the probability of a randomly selected card being an ace and a spade. Remember, the word "and" suggests we are using multiplication rule. So we are using this formula here. We'll let probability of A be the probability of a card being an ace, and we'll let P of B being the probability of a card being a spade. And we want to know the probability of randomly selecting one card out of the 52 in the deck and it being an ace and a spade. Now, common sense, you might just be able to figure this out without needing to do the math. You know, okay, well, there's only one ace and a spade in a deck of cards, so it's going to be 1 out of 52. That's easy. And you'd be right. I just want to show you the math behind it when we do problems that are more complicated than one you can just solve in your brain with mental math intuitively. Okay, so what is the probability of getting an ace? 4 out of 52. There are 4 aces, so 1 out of 13 or 4 out of 52. Doesn't matter because we're doing multiplication. What is the probability of a card being a spade? Well, it'll be 1 in 4 or 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 out of 52. Multiplying those two values together, 4 out of 52 multiplied by 13 out of 52, you get 1 over 52. And that would be your answer. And it's the same as just saying, well, only one card in a deck of cards is an ace of spades, so 1 out of 52. So you can just solve that one intuitively or mathematically, but I want you to be able to understand the mathematics behind it. Okay, so that we just did multiplication rule with one trial. Now we are going to talk about the multiplication rule with 2 trials, meaning you do one trial first, record your answer, and then you do a second trial right after. So the notation here is that probability of P of A and B is the probability of event A occurring in the first trial and event B occurring in a second trial. Okay, so then from here, it is 2 branches. It can go into independent and then dependent. So first, we talk about independent. 2 events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. So if A and B are not independent, then they were going to be dependent. Nothing too crazy right here. Let's talk in an example. So what makes them independent or dependent? Well, do they depend on one another, obviously? So say I roll a dice and I get a 3. If I roll that same dice a second time, the outcome of that roll is completely independent of the outcome I got from roll 1. So the probability of rolling any particular number does not change. So those are independent of another. You are saying that past outcomes have no effect on future probability. So that's independent. They have no bearing on one another. What you roll the first time has no effect the second time. If you have a boy for your first child, when you have that second child, the gender of the first child has no bearing on the gender of the second child. Now let's talk about a dependent case. So say I randomly select a card from a standard deck and I get an ace of clubs. If I keep that ace of clubs and draw another card from the deck, the probability of me drawing a red card is going to be slightly higher since it is dependent on the outcome of the first drawing. Now, when I draw that second time, there's only 51 cards left in the deck, and there's a slightly higher chance of me getting a red card now that there's only one less black card in circulation. So, does that make sense? Let's look at that a little further in example. So, probability of A and B. We talked about that. It's a probability event A occurs in the first trial and event B occurs in the second trial. So now here we have the two sub-equations. So if they are dependent on one another, then we say the probability of A and B is equal to the probability of event A and the probability of B slash A. Or what does that mean? Well, B slash A represents the probability of event B occurring after it is assumed that event A has already occurred. And that might sound a little complicated, but I think it makes sense intuitively, and we're going to look at an example. And then if the events are independent of one another, think about the case of having children with certain genders, or think about rolling a dice. If they are independent of one another, then the equation is a little simpler, and it's just the probability of A multiplied by the probability of B, similar to the single trial example we did a little earlier. Okay, so let's look at an example. Multiplication rule. What is the probability of flipping two heads in a row? Okay, is this dependent? Well, first off, you really should be asking yourself, is this multiplication rule or addition rule? And you'll find that this is the multiplication rule. We are dealing with two trials, so it's going to be the multiplication rule. Are they dependent or independent? Well, I gave you the answer, but you should be able to realize that it's independent of another. If I flip a coin and it's a heads, if I flip that same coin again, the probability of it being a heads or a tails doesn't change. So it's independent. When it's independent, we're looking at this equation right here, and it's just going to be that the probability of event A and B occurring is just going to be the probability of event A multiplied by the probability of event B. So what do those probabilities events mean? Well, we'll let A be the probability of flipping a heads on the first flip of the coin, the first trial. And then we'll let event B be the probability of flipping a heads on the second trial. So what is our answer? It's going to be 0.5 multiplied by 0.5 is 0.25. So the probability of flipping two heads in a row is going to be 25%. Okay, let's look at another example. What is the probability of drawing two consecutive red cards in a standard deck? And we are saying that we are without replacing the card after the drawing. Basically, pick a card, any card. Then you pick the card, look at it, and then we're not replacing it. You're not putting it back in the deck. So that means it's a dependent case, since whatever card you draw the first time affects the probabilities of the card you draw the second time. So since it's dependent, it's going to be this equation right here. We'll let A be the probability of drawing red card first, and we'll let B be the probability of drawing a red card second. So, probability of A, well, how many red cards are there? Well, you can say it's 1/2, or if you want to be include all the outcomes, it'll be 26 out of 52. 26 out of 52 cards are red. So once you draw that first red card, imagine the scenario of me holding out a deck of cards and you picking one, looking at it, and it being a red card. So then you put that card in your pocket. So now I'm holding out the remaining cards, and I tell you to pick another one. Well, how many cards are left? Well, we start with 52, you took one, now there's 51 cards left. How many red cards are left? Well, we started with 26, you took away one red card, so now there's 25 red cards left. So that is what you're dealing with. So PB of A is going to be 25 out of 51. So do the math right there, and then you get 24.5%. So slightly less than 25%, 24.5%. Okay. So let's do another example. Screening drugs and the basic multiplication rule. 50 test results from the subjects who use drugs are shown below. So 50 people who use drugs are shown below. So 50 people total, 45 of them had a positive test result, and then 5 of them got really lucky and got a negative test result, even though we know that they use drugs. Okay? So let's look at A. If 2 of these 50 subjects are randomly selected with replacement, find the probability of the first selected person who has a positive test result and the second person has a negative test result. We'll go to B after. So now we are talking with replacement. So we want to know the first selection has a positive test result. Okay, so that's easy. It's just going to be 45 over 50. And since it is with replacement, we are saying that these are independent. So the second selection, which is 5 negative results among 50 people, is going to be 55 over 50. So now apply the multiplication rule as follows. Since we are dealing with independent trials, without replacement would be dependent. With replacement would mean independent. So we have 45 over 50 multiplied by 5 over 50, and then we get 0.0900 or 9%. There is a 9% probability that if you select 2 people at random among these 50s, the first person has a positive test result and the second person has a negative test result. And now B. We want to look at B, which is repeat part A by assuming the 2 subjects are selected without replacement. So what's the difference between with replacement and without replacement? It has to do with if it's independent or dependent. Part A, we said with replacement was independent because now the probabilities aren't changing regardless of what you select on your first trial. But without replacement, think of you have 50 people in a claw machine, and then you have your claw machine go, it grabs them by the head, and now they're out of circulation. Then you throw them off to the side. So when you do your second trial, now you only have 49 people left in the claw machine. Okay, so let's look at it. So without replacement of the first subject, the calculations are the same as part A, except that the second probability must be adjusted to reflect the fact that the first selected person was positive and is not available for selection for the second trial. So the first trial is going to still be that 45 over 50 because the first person that we selected is a positive test result. So when that claw machine came down, it selected a person at random. 45 out of 50 probability that that person had a positive test result. But once he's out of circulation, what do you have left? You have 5 people who have a negative test result out of 49 test subjects remaining. So the probability becomes 45 out of 50 multiplied by 5 out of 49, which would give us 9.18%. So slightly higher than, where are we? What we did from part A, which was right here. Oh, right here. Sorry about that. Okay. Whew, this is a long section. So here is just another summary of what we just talked about independent events versus dependent events, and then giving you some examples of each. Okay. Treating dependent events and independent. This is just a general FYI. I don't know if this will come up in the questions that I'm going to quiz you on, but it's good to know. So if you are sampling without replacement and the sample size is less than 5% of the size of the population, you can treat them as being independent. Basically saying, if you're talking about a population of a huge number of people, and even if you have without replacement, which would normally be dependent, you can treat it as independent, just to make calculations a little bit easier. You're saying that the change in probabilities by treating it as independent is pretty much negligible. Okay, so let's look at a quick example. Assume that 3 adults are randomly selected without replacement. So you're not risking the probability of interviewing those same 3 people three times. Once you interview that adult, they're no longer going to be looked at again. So you're saying that they are without replacement. So we are randomly selecting 3 adults without replacement from the 247,436,830 adults in the United States. Now we say that assume 10% of adults do drugs. Find the probability that the 3 randomly selected adults all use drugs. So because they are 3 randomly selected adults without replacement, they're independent of each other. The first time we're going to have this many adults, but once that one person's done, this would go to 829 and 828. But we're going to say that that is such a small difference. Since it's less than 5% of the total population, it just is going to make the calculations cumbersome and overly complicated. So we're going to say, hey, even though they're technically dependent, we're going to treat them as independent. So once we're independent, it gets a lot easier. So we're going to say probability of the first person uses drugs multiplied by the probability of the second person uses drugs multiplied by the probability of the third person uses drugs. So 0.1 times 0.1 times 0.1 gives you a 0.001 probability that all 3 selected adults use drugs. Okay, these are hard to do in one shot without any pauses or edits. Okay, next example. We're talking about redundancy for better safety. Okay, so modern aircrafts are highly reliable. You probably have heard stats that show you that traveling by air is actually the safest way of traveling per mile traveled. And even though many people are afraid of airplanes, the numbers show that the probability of you getting seriously hurt or even killed in a car are actually a lot higher. And trains, I believe, were even higher. Aircrafts were the safest. But yet people are often very afraid of flying. Anyway, so modern aircrafts are highly reliable, and one of the reasons for that is that they use redundancy with safety features. Whereas, you'll have 2 engines on a plane instead of just one. So if one fails, the other will work. So for example, the Airbus 310, which is a type of aircraft, has 3 independent hydraulic systems. So if any one of them fails, they can maintain full control with the other ones as well. So we will assume that for a typical flight, the probability of a single hydraulic system failure is 0.002. So if the Airbus 310 were to have 1 hydraulic system, what is the probability that the aircraft's flight control would work for a flight? Okay, that's easy. Since we're only dealing with 1, and the probability of it failing is 0.002, the probability of it not failing is going to be the complement of that. So 1 minus 0.002 gives me 0.998. Basically, there's a 99.8% chance that the aircraft will not have any kinds of failures. Pretty good, but not good enough for these aircraft lines. So let's look at part B. So given that the Airbus 310 has 3 independent hydraulic systems, what is the probability now that a flight can be maintained with a working hydraulic system? So they are independent trials, since the probability of the first one failing and the second one failing and the third one failing are unrelated to one another. So we are looking at an independent system. So using the multiplication rule, we have 0.002 multiplied by 0.002 multiplied by 0.002 equals 0.0000008% chance that all 3 of them fail. So if we want to know the probability that none of them fail, it's going to be the complement of that. So 1 minus this, which equals a 99.9999992% chance that the flight moves safely. So by adding 3 hydraulic systems instead of 1, you don't reduce the risk by, oh, it's 1/3 of, it's 3 times as safe to have 3 extra systems. No, it's actually a factor of 1 over 250,000. So by having 3 independent hydraulic systems, risk is dramatically decreased and safety dramatically increased. Okay, so the summary right here is for addition rule. The word or suggests addition. And then when we're doing that, just make sure that you're adding those probabilities in a way that you only count each outcome once. And then with multiplication rule, the real key word is the word and. And then you look at if they're independent or dependent trials, and then do the equations that follows. Okay, this is a very important section. I know it was long, so thank you for sticking with me. And any questions, always email me. Thank you.